So welcome back, everyone. So today I'll show you some tools by which you can figure out eigenvalues of nice graphs that have some kind of regularity in them. And we'll do a general theorem about equitable partitions and eigenvalues of quotient matrices and eigenvalues of graphs. And then if we have time, we'll talk about eigenvalue interlacing and the two types of interlacing that are commonly used in graph theory. So I'll start with the first topic, so equitable partitions. And quotient matrices. So I'll give you first a definition that may seem a little bit out of the sky, out of the blue, but then I'll do some examples and we'll kind of proceed towards the main result for this part. So definition. As before, let's have gamma be an undirected graph. Now a partition, let's call it pi, of the vertex set into sets v1 ... vk. So a partition, I'll call the partition, I'll give the partition name pi, or v into sets v1, vk. So I put this dot here just to signify that the subsets v1, vk are pairwise disjoint and that they're all non-empty, okay? Is called equitable if there are some numbers bij, let's say real, they're going to be, let's just put natural numbers or 0 for any I and j between 1 and k, okay, such that the following happens. For any I and j, so when I say for any I and j, we're going to think about for any vi and any vj. In my picture, they look different, but they could be equal. I'll deal with that in a second. So for any I and j don't have to be distinct. For any vertex x in the part vi, so no matter what vertex I pick in the part vi, if I count the number of neighbors of the vertex x in the part vj, this is always going to be a constant, which is going to be this number bij. Okay, so I'll put it this for any x, the number of neighbors of x that are contained in vj equals bij. Now, in general, I will denote the set of neighbors of x. So I will use this notation. Gamma of x will be the set of vertices y, such that y is in v and y is adjacent of x. So this is the neighborhood of x. So this condition here, for any x in vi, the number of neighbors of x that are contained in vj equals bij, you can write it as the cardinality of gamma x intersect vj equals bij. Okay, so I'm sorry, it's a little bit again, it's a little bit abstract at the beginning, but I'll do some examples and hopefully we'll kind of get comfortable with this definition. Again, just a general picture. You have like some partitions v1, v2. Like I said, you may have vk here, and then you have your vi and your vj, and so you have the partition of the vertex set, and the condition that I said, if I pick a vertex here and I count the number of neighbors here, this is always going to be bij. And this works for every I and j. So if I look from here kind of this way, this number will be bji. Okay? Also, if I take I and j to be equal to each other, what does it say? It says that for any x in vi, the number of neighbors of x that are contained in vi equals bii. So it means that the subgraph induced by the vertices vi is a regular graph of valency bii. So inside here, this one is b11 regular, b22 regular, and so on. Okay, so an equitable partition, you have this partition into various blobs. Okay, inside each blob you see regular. Okay, when you look there you just see regular, induced regular, and if you look between any two parts you see what is called biregular. So from one side to the other the degrees are the same, vice versa. Okay, so you see here it doesn't mean that if I take, for example, if I take another vertex here, it doesn't mean that the neighborhood of this vertex and this vertex, so this was my x, if I take some x prime, the condition doesn't mean that x and x prime have to have the same neighbors, but they have to have the same number of neighbors in here. That's all it is. So this one could be here, but it's also the same number, bij. Okay? So let's do some simple examples. Okay. So, everybody's favorite example, the Peterson graph. Okay, can we find some equitable partition here? You know, k, whatever your k you want. Obviously, you may want a k smaller at the beginning, just so that you. Let's see. Can I find a partition with k equals 1? Equitable partition with k equals 1. Which one is it? The entire set. And why does this work? Because it's regular. So this is not something specific to the Peterson graph. Every regular graph, you will have an equitable partition into one part, the vertex set itself. So this is not just for a Peterson graph. For every regular graph will have. Okay, k equals 2. Yes, the cycle on the outside, so V1 is the 5 vertices on the outside cycle, and V2 is the rest, V minus V1. Okay? Now, these entries, these Bij entries, these are very important, and we will put them, so if a partition is equitable and we have these numbers, we collect this number into a matrix, into a k by k matrix. Okay, so if I follow up that definition, if pi is equitable, then the matrix, I'll call it B, whose entries are Bij, is called the quotient matrix of the equitable partition pi. Okay, so in this case, so let's do it here for the partition k equals 1. What is B? Let's call this B1, okay, because it's the first one. What is this matrix? Eh? Just K. It's just a matrix. It's a 1 by 1 matrix with K. Okay, nothing. For here, what is B2? It's going to be a 2 by 2. Yeah. 3. Okay, so it's going to be K for any K regular graph. So that's why I was, yeah, thank you. So it's 3. For any K regular graph, the partition into the set itself will be just K.
We use K here.
We use K, oh, okay. Yeah, so forget about K3, okay? Okay, thank you. B2. What is here? 2, 1, 1, 2, okay? Okay, can you think about a partition here into 3 parts? Equitable partition into 3 parts. So you see, you kind of have to, I mean, people, so in this case, it's about some kind of symmetry and so on. In general, it's going to be about regularity. So there is a kind of interplay between symmetry, implies maybe regularity, not necessarily. But you have to, try various partitions. The easiest one the one that I know is you take a vertex. Now, there's another way. This is a picture that you get conditioned to use for Peterson graph, because this is a picture you see all the time. Now, you can think of it differently. You have a vertex, you have the neighborhood. Peterson graph has no triangle, so there are no edges here. Then each vertex has degree 3, so there are 2 edges down. Now, Peterson graph has no cycle C4, so all these vertices at the bottom, there are 6. They're all distinct. And at the bottom, what you see, it's something like this. Now, this is the weirdest way of drawing what kind of a graph? Yeah, but the one at the bottom, what is at the bottom? What do you see about these 6 vertices? What do they create? Yeah, it's too regular. It's 6 vertices, so there are 2 choices. 6 cycle. It could be 6 cycle or 2 triangles, but it's definitely not 2 triangles, so it's 6 cycle. So now, if you have this picture in mind, you can think of the following partition. This is V1. This is V2. And this is V3. So let's see if it works. So this is a partition with K equals 3. And let's call this B3. The entry here, does everybody follow? Yeah, okay. So the entry in the position 1, 1, you look here and you see what is, it induces a regular graph of valency, 0. From 1 to 2, every vertex has how many neighbors? 3. And from 1 to here, 0. And you continue like that. If you look at the row of V2, this way is going to be a 1. Inside, you see 0. And then down, you see 2, and so on. From here to here, 0. Back is going to be 1, and it's going to be 2. Okay? Yeah. Now, so the reason I wanted to give you this example, and maybe I'll give you a few more examples in a second, is that if you just do these 2 examples, you may think, okay, this matrix B, symmetric, and so on. But here is definitely not symmetric. So the matrix B in general is not going to be symmetric. So just remember that. Okay. Okay, so I have the definition. Let me erase here. So I'll do one more example, and then I'll give you the main theorem. So let's just do one more example. So I gave you examples of equitable partition. Maybe sometimes the partition is not equitable. So let's see if we can tell in that case. So let's stay with Peterson graph. Okay, so let's say this is one part. Let's say this is another part. And let's say this is a part. So essentially what I show you here, let's say, again, let me call this W1, W2, W3. So what the partition that I'm taking is the partition from an edge, the vertices. So I start with an edge, that's W1, then you have this, then that's W2, and then this is W3. The partition that I gave you here, it's the same, it's a distance partition, but from a vertex. And this one was equitable. I pick a vertex. This is the only set of vertices at distance 0 from where I start, distance 1, distance 2, okay? Here, I try to do the same thing from an edge. I start with an edge. What are the vertices that are adjacent to one of these, and then so on. Is this going to be equitable? Sorry for... it could be. Maybe I'll leave this. Where are we with exercises? 13? Okay. Exercise 14. Figure out if this is equitable. Okay. All right, so let me give you now the main result, and hopefully you'll be convinced why this is useful. Well, first let me give you a few lemmas, just so a proposition. Okay. Yeah, before proposition, let me give you a definition. So I need something. So the thing that I'm going to show you here is that this matrix, the eigenvalues of this matrix, are going to be real, even though this is not a symmetric matrix. And these eigenvalues are going to be eigenvalues of the big graph. Okay. So to do that, we have to do a few things. So, as before, let's say we have assume that pi v v1 union vk is a partition of v for a graph. Now we can collect the information of this partition into a matrix, and the matrix is going to be very simple. So the characteristic matrix P of the partition pi. At this point, the partition doesn't have to be equitable or anything. For any partition, you can define this characteristic matrix is the n by k matrix. So it's a tall matrix whose columns are the characteristic vectors of v1, vk respectively. So maybe let me give you a smaller example so you can see what this is. Okay, so let me give you a smaller example here. Let's take this graph. Sometimes it's called a bow tie graph or friendship graph, or okay. So I will show you like this this characteristic matrix for two partitions. So let's do first one partition where v1 is here and v2 is the rest. So v1 is this vertex here. Let's call this vertex, I don't know, x. And v2 is v minus x. So this partition, let's call it pi, this partition is equitable, and you can find the characteristic, the quotient matrix of this partition is going to be 0 in x, then 4. Inside the rest, you see from outside towards x, everybody has 1, and then 1. Make sense? So that's the equitable. Now I can do another partition let me draw this a bit differently. So this is x. Okay, let's call this now u1. This here is u2, and this is u3. So the v2 from before, I just split it into two parts. Okay. So you have to look, is this equitable? Inside each part I see regular, between each part I see biregular. So let's say if this is pi prime, v equals u1 union u2 union u3, the b pi prime equals 0. Now from here to here you get 2, from here to here you get 2. From u2 back, you get 1. Inside u2, you have 1. And here you have 0. u3 to u1, you have a 1. u3 here, 0, and you have a 1. Make sense? Okay, so these are the quotient matrices. And let me show you now this matrix P in each case. So P of pi, so it's going to be a tall matrix. So here I have 5 vertices. And now maybe it helps me, I will change the name of these vertices. Let me call this 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Now for pi, I have two parts, v1 and v2. So here I will have 1, 2, 3, 4, 5. So this is going to be a tall matrix. And the two columns are going to correspond to v1 and they're going to correspond to v2. Because I just have two parts, in general k parts. And then the characteristic vectors of, so here, let me put this 1, this is 1. The characteristic vector of v1 is you just put a 1 where you have elements in v1. So in this case, it's just going to be 1, 0, 0, 0, 0. And the other one, the characteristic vector of v2 is this one. Okay, so it's nothing more than just a collection of. And now here, p prime, the same thing. You have u1, u2, u3. The same labeling, 1, 2, 3, 4, 5. 1, 0, 0, 0. Then u2 is 2, 3. So it's going to be 0, 1, 1, 0, 0. And then 0, 0, 1, 1. Make sense? So this is a characteristic matrix of, so this is a tall matrix. This is as tall as I can make it. So this is P. And you have N here, you have K here. And here you're going to have a characteristic vector of V1 all the way characteristic vector of Vk. Okay? And because this is a partition, what do you get immediately about these columns of P? They're orthogonal on each other. Yeah, the distinct, different columns are gonna, yeah, very good. Okay. And the other thing, what do you get about, so P transpose P. So this is kind of a bit more than what I just asked you. So this is, in P transpose P, you will keep track of the inner products between the columns of this matrix. So what you will get? What do you get off diagonal? Off diagonal. Off diagonal you get 0. And on diagonal, what do you get on diagonal? The size of each part. So this is going to be a diagonal matrix where you get cardinality of V1, cardinality of Vk on each part. So keep that in mind because we will use it. Okay? All right. Okay, so let's start now with the first proposition that connects equitable partition with these matrices. Okay, so if pi is an equitable partition, of gamma with quotient matrix B and characteristic matrix P, then two things will happen. A times P will equal P times B. So A here, again, A here is the adjacency matrix of the graph. Okay, so A interacts with B via this characteristic matrix, P. And second, obviously you like to get your hands on B from here in terms of, you know, to get rid of this P. But P, you cannot just, it's not a square matrix. But you can do some, we'll show it in a second. It looks a little bit P transpose P, which is this one here, inverse times P transpose times AP, this equals P. Okay, so that's the proposition. Now, when you see matrix multiplication, maybe some of you have this kind of vision that, you know, people who do like matrix analysis, sometimes they can see, okay, what the result is very quickly. But even if you're unable to do that, we can just do some simple calculation and we'll try to figure out what happens. So let's prove one, because if you prove one, we'll get two very immediately. Now, let's see first on one, let's draw a picture to see what happens on one. So in one, we have the big matrix A. So we claim that this big matrix A, you multiply it by this tall matrix P, and the claim is that the result should be an n by k matrix. And the claim is that that n by k matrix is the same as if I take the same matrix P. Remember, we saw some kind of equation like this yesterday, a little bit, and then you multiply it by this. Okay. All right, so proof. So what do we want to do for one? So we want to figure out what an entry is here. Now, when you calculate this matrix product, you take a row of A, you multiply it by a column of P. What is a row of A correspond to? To what kind of object? A vertex in the graph. So I will take a vertex in the graph, let X be in V. Now, what does a column here correspond to? One of those parts in the partition. So they're V1, V2, Vk, so I'll pick one of them. So let X in V and J in 1, blah, 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 K. Okay, so now what we're going to do is we're going to calculate the entry in this matrix A times P in the position Xj, and then we'll calculate this one in here Xj, and we'll see if they're the same. If they're the same, we're done. Okay, so let's see. Now what will help us is X is in V, and what will help us is to know exactly the position of X. So as before, V is a V1 partition Vk, and we just pick X in V, so X is going to be in one of these subsets. So we just have to give a name to that subset. So let's say this is going to be Vi, this is X, and this is going to be Vj. Okay, so denote, well, let's say, well, I'll just say denote by I, well, let me phrase it again. We'll assume that X belongs to Vi for some I in the set 1 to K. Okay, so now we start calculating. We have that. AP in the position xj. So what will this be? It will be the row of x in a product with a column of j. So it's going to be, so what labels that? That's going to be labeled by a y, summation over all y in V, AXY, PYJ. So again, here what I'm doing is I'm taking, let's say this is the row of x, and I'm taking a column of j, let's say it's at the end, and I'm taking the inner product to C1. So here, AXY and PYJ, what kind of numbers are they? 0 or 1. So you only have to figure out here who survives in this product. So you have to figure out when both of them are going to be 1. Okay? Now it's easy. AXY, when do you have a 1? When y is adjacent. So I can change that to summation over all y is adjacent to x, and I get rid of this. So let's do it in these steps. PYJ. And now, this, when is this going to be 1? When y is in Vj. So this is the sum over all y adjacent to x, and y in Vj. Of what number? 1. So do I know this number? The partition is equitable with quotient matrix Bij. So I'm counting for x, I'm counting for each neighbor that it has in here, I'm counting 1, so Bij. Very good. Okay. So now let's calculate. We have that. Also, let's see PBXJ. Okay. So now we're going here. It's a different type of multiplication. Again, we take the x. Let's say it's here. This is x, the first vertex, and now we multiply by j. So here you see it's an inner product of n by n vectors. Here it's an inner product of k by k vectors. So first, let's write it. Summation over. Now, what are these things labeled by? Partitions. So summation over, I use I and j, so let me use L. L equals 1 to k of PXL BLJ. So L basically keeps track of L. L is here. It goes from 1 all the way up to k. It goes from 1 all the way up to k. The same, well, here it's not quite the same as before, because BLJ, it's either 0, well, it's either 0 or non-zero. PXL, it's either 0 or 1. So you might as well just, you ignore the zeros, you just have to pick up when is this going to be 1. When is this going to be 1? For which L? So it's for the L where x belongs to, which we gave it a name already, so that's going to be I. So this is going to be PXI times BIJ. What is PXI? X belongs to VI, so that's going to be 1. And what is BIJ? BIJ. Okay? Very nice. So actually, more is true. The partition is equitable if and only if AP equals PB. So I just showed you if it's equitable, AP equals PB. you can, we put it to the exercise to show the converse, okay? Like if AP equals PB and P is a characteristic matrix, then something else. But for now, let's leave it here. So 1 is proved, okay? For 2, you can essentially, you try from here, you want to get rid of this. You cannot multiply by P, because P doesn't have an inverse in general. So you make that P into a square matrix. So we have, I'll just write it informally like this. AP equals PB. You multiply to the left by P transpose. And the reason you multiply to the left is that you create here something that is invertible. And now you can get rid of it. So then you multiply to the left by the inverse of P transpose P. So you get this weird formula and you get B. The key one to remember is this one. I mean, we'll use this one in a second, but if you get this one, then this one it is. So you have to remember that equitable partitions essentially will be the same thing as this. And again, we kind of saw this equation earlier about yesterday about these A invariant subspaces and so on, and that's going to be I'll write that. I'll give you another proposition in a second. Any questions? No? Okay. Okay. Okay, let me see. Okay, so I'll put this here in a proposition before we write down the main result. So a partition phi is equitable if and only if so I'll write it this way: the column space of P, of its characteristic matrix, is A invariant, which is the same thing as okay. So we proved one implication. We proved that if it's equitable, then AP equals PB. Now I'll leave it the other implication. So this one we did it, done. This one is exercise number 15. There. Okay. VP. Okay, so let me write down here the main theorem. So theorem, as before, let phi be an equitable partition of V with quotient matrix P, B, quotient matrix P. Then the following happens. Then 1, the characteristic polynomial of B divides the characteristic polynomial of A. So this will imply that B has real eigenvalues. Okay. You can kind of get it from here a little bit, but yeah. And then the second one it's actually also true that we didn't talk about minimal polynomial, but the minimal polynomial of B divides of A. I will just prove 1, okay? So I have that, I have that. Let me erase here. Okay, proof. Okay, so the key thing is this result. This is the key to us. So again, what we have is we have this A big matrix times the P equals, it's a linear combination of the columns in P, okay? Okay. Now, what we'll do is we'll extend a little bit the P. So if you look at the columns of P, you observe that they're pairwise orthogonal. So any two different columns are orthogonal on each other, so they're linearly independent. And what is the first result you learn in linear algebra? Yes, you can always, linearly independent, you can always extend to a basis. So that's exactly what we're gonna do. So let Q be n by n minus k matrix such that the matrix P and Q is invertible. So the columns of P are linearly independent. You add more columns to them, so you make a basis. These are the Q. So this is P was K, and now you just add n minus k columns any way you want. Okay, your favorite procedure. Okay, everybody follows? So yeah, okay. So okay, so what we want to know is, okay, what happens? I know AP, I know what AP is. Let me see what happens if A meets this matrix PQ. So we have that. A times PQ equals AP times AQ. Okay? Now, AP is PB. What is AQ? Well, AQ is going to be something, some kind of matrix, some columns. Now, this PQ matrix, this is the one that has, like, the columns of it are the bases in your space. So any columns you give me, I can write it as a linear combination of the P's and the Q's. So how are we going to phrase this? Let me write it down. So before I do this calculation, let me insert something here. Because the columns of PQ are form a basis, there are some matrices, let's call it C and D, such that AQ is going to be PC plus QD. So this is just writing that when you multiply A by the columns that you get here are going to be a linear combination of the columns in P and the columns in Q. Okay? So now with that, AQ, it's PC plus QD, so I write it here as PC plus QD. Remember, like when you have a matrix and you multiply it the simplest form, if you take a matrix and you multiply it by a scalar to the by a vector to the right, you get a linear combination of its columns. Multiplication to the right means linear combination of the columns. So that's what happens here. Okay? So AP, AQ, okay? Now here, this is the part where we have equitable partition. You can replace AP by PB. And then this is PB, PC, QD, and you can rewrite this as PQ from the left, and this is the matrix BC0D. PQ B0, PQ CD. Okay, so let me rewrite it on the right. So A times PQ so I'm not going to write the dimensions. I mean, you can figure out the dimension. B is K by K, C and D, okay? Now, PQ, the columns of PQ are bases, so PQ is what kind of a matrix? It's invertible. So I can, so what does this mean from here? Which matrices are similar to each other? Yeah, so this implies that A and BC0D are similar. So if you're similar, your characteristic polynomial is the same. But what is the characteristic polynomial of a matrix like this? The product between the characteristic, okay? So we're not going to prove that, but do it if you're not sure. So this implies that the characteristic polynomial of A equals the product. I'm writing this because I haven't given a notation for the characteristic polynomial, so I'm not going to do it now. The product of the characteristic polynomial of C and the characteristic polynomial, of B, and the characteristic polynomial. Of D. So that proves what we need. Okay? So I leave the second part as exercise 16. The minimal something polynomial. Okay? Okay. Maybe also another exercise from here. Without doing all this stuff, so from what we showed here, we get that B will have real eigenvalues because the characteristic polynomial divides something that has only real eigenvalues. But from here, let's do exercise 17. Prove that B is similar to a symmetric matrix. So try to prove this with, okay? So that will also tell you that you have real eigenvalues, but I will tell you less. Yeah. Okay? So this is the important thing about equitable partition is that you can get your hands on something of the big graph using something from something small. You make an equitable partition into small parts, you figure out what happens, and then you can get information about the big graph. So let's do some examples for the graphs that we did earlier. So I did this here. I'll erase here. So let's do this. Come back to our example. This bow tie. We had two partitions. The first partition into two parts, pi. I'll just write down the quotient matrix 0, 4, 1, 2. Okay. What are the eigenvalues here? Let's say lambda 1 of, you just calculate, okay, so I'll, P of B of pi is a determinant of xi, so I'll introduce this minus b pi. So what is this going to be? X times x minus 2 minus 4, so it's x squared minus 2x minus 4. Yeah. Thank you. Thank you. So x, thank you, x minus 1. Okay, thank you. Very good. Yeah. Okay, the discriminant is 17, I think. B squared minus 4ac, okay? So then the two roots, lambda 1 of b pi is going to be 1 plus square root of 17 over 2, and lambda 2 of b pi is going to be 1 minus square root of 17 over 2. Okay, not something that maybe you were expecting, but so these are, so what do you see? You get, this partition is equitable. I get two eigenvalues. By the previous theorem, these two eigenvalues will be eigenvalues of this graph. Good thing, but it doesn't give you the whole spectrum. Because you're supposed to have 5 eigenvalues. We only got, yeah, 2. We'll see in a second how we do that. Now, what about this partition? The other one that we did, where we had partition pi, we had this, we had this, we had this. This b prime was 0, then you had 2, 2. 1, 1, 0, 0. No. 1, 0, 1. Okay. Okay. Now, I'll leave it to you. Exercise 18. See, I can do 2 by 2 matrices, but you can do 3 by 3. Okay. Just see what you get, because it's actually interesting. So you will get at least one more eigenvalue, but see how it is and see if they relate to this one. Okay. It's actually a good thing to try to see if there's a connection between what you got here and what you're going to get here. Okay. All right. Now I'll state one more thing and then we'll stop. So this is good. I'll just erase here. And we can do applications of this maybe in the afternoon. So the last one. So this is the second theorem. Okay, how do you get your hands on more eigenvalues and actually on eigenvectors? So the same thing as before. Let pi be an equitable partition with quotient matrix P and characteristic matrix P. Okay, so 1, you can get eigenvectors of the big matrix easily from taking from the eigenvectors of this matrix by doing something called a lift. So here's what I mean by that. If V is an eigenvector of B, okay, so let me write it here. BV equals, let's say, some theta times V. Okay? Then PV is an eigenvector of A corresponding to the same eigenvalue. So what will happen if BV equals theta V, APV will equal theta PV. And these are, so this eigenvector, so here essentially what you can think about, I'll show you a picture in a second, V lifts to an eigenvector PV in the big matrix, but that's not important now. Okay, and the second thing, let me write it. I'll write it here. The second part says the following, that the eigenvectors of A can be split into two parts. Part A, the eigenvectors of A that are constant on the sets of the partition pi. And these ones are exactly these PVs. These are the PV eigenvectors where V is an eigenvector of B. So this will be constant on the sets. So you have this type of eigenvectors that you get from B, and the remaining one, this will be the eigenvectors of A that sum to 0 on each set of the partition pi. Okay, so I'll leave it like this for now. So let me show you what we mean here in terms of this example. And then we'll finish. So B, okay, so we found two eigenvalues. So lambda 1 of B, what was it? 1 plus root of 17 over 2. And lambda 2 of B is 1 minus square root of 17 over 2. Now, for this lambda 1 of B, let's say we have BP times some vector, let me call it here entry A1, A2 equals this lambda 1 of B times A1, A2, okay? So the part 1 tells you that you see like this first part corresponds to this vertex. This second part corresponds to these 4 vertices. So what we do from this eigenvector, we put A1 here, and then you're going to put A2, 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 A2 here. And this is example of this vector PV. And this eigenvector here will be an eigenvector corresponding to this eigenvalue of B or of A, okay? And you do the same thing here. So whenever you have an eigenvector for this B, you just, I mean, let's think here what this PV gives us. So P is going to be something like this. So you have V1, blah, 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 VK. And here you have maybe the same thing, A1, blah, 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 AK. Okay, so when you do this multiplication, you have to. What's going to happen is that this A1, how is it going to work? Yeah, so basically, your vector that you will get here is you'll get A1 in V1, A2 in in V2 and AK in VK. That's exactly what happens here. Now let me show you this very quickly, just so that we understand. So you have BV equals theta V, but you also have AP equals PB. This is the key, again, the key equation. So what you do, you multiply here to the right by V, and what you get is APV equals PBV. But now this is what happens. So you substitute here, and so what you get is A times PV is going to be P times theta V, and is going to be theta times PV. So everything works in your favor, and you collect your. So these are the easy eigenvector to collect, because ideally you will have here a small enough matrix that you know everything in there, 2 by 2, 3 by 3, I don't know, even maybe bigger, but much smaller compared to the size of the big graph, and you will get these eigenvectors that are going to be constant on the size of the partition. Okay, and I'll stop here because it's time, and then I'll tell you about this in the afternoon, and we can try to do more example to figure out the other values. I have another half. I started at 9:30? Okay, then I continue. Okay, I'm sorry. Somehow I thought we started at 9. Yeah. Okay. So, okay. So these are the easy ones. You just lift. Now, how about these other ones? So how is that going to work? Let me see. Okay. So the ones that you have here, so these are these are going to give you a basis of this of the column space of P. Okay. So the column space. These eigenvectors will give you a basis of the column space of P. Okay? Now, this is a basis of eigenvectors. Where are you going to find the other eigenvectors? You're going to find them in the orthogonal complement of the column space of P. So you're going to look for eigenvectors that are going to be perpendicular to the column space of P. But if you're an eigenvector and you're perpendicular on the column space of P, you're going to be perpendicular on every column vector. And the column vectors are what? Are the characteristic vectors. So if you're perpendicular on them, it means that you must sum to 0 on each. And actually, there's more here. Let me give you something. So. Right here. Let me erase here. So in B, so the eigenvectors, so I'll just write it again, the eigenvectors that sum to 0 on each class on each set of the partition pi. And these eigenvectors, because they sum to 0 on each of these parts, are also eigenvectors of the matrices obtained by, so let me do a picture here. This is the matrix A. Let's say the V1s are arranged like this. V1, V2, Vk, V1s, V2, Vk, okay? obviously the V1s and V2s, they may not be consecutive vertices, but like reorder it such that they're consecutive and so on. So this is A11, this is A12, and so on. Like here, if I have I here and I have some J here, this will be Aij, okay? So these eigenvectors are also eigenvectors of the matrix you obtain from A. By replacing these blocks Aij by blocks of the form Aij plus some constant Cij, all one matrix. So because they're going to be perpendicular on these sets, where the J is the same dimension as this is Aij. Okay, so you can think about that way. Let's do an example here. Okay, so here the eigenvectors that are constant, we found all of them because they are the ones that look like PV, and we found 2. Okay, so now we're going for these eigenvectors that sum to 0 on each part of the partition. Okay, so let's try to figure out what they are. Okay. Huh?
What are the CHs?
Like for some appropriate, for any like constants that you want. So sometimes you will use some constants so that in the Aij you may want to create zeros, so that you make your matrix a bit easier. So so for this matrix, for this graph, the adjacency matrix, or A of gamma, how does it look? Like you have, let's put the vertex, the V1 is first, V1, V1. You have 0, you have 0. Now V1 is adjacent to everything, 1, 1, 1, 1, 1, 1, 1. And here you have the V2, and this one is this perfect matching. So it's 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, something like this. Okay. So in this situation, this is the matrix A11. This is the matrix A21. This is the matrix A12, and this is the matrix A22. Okay. Okay. So we found so you're looking now on things that sum to 0 on each part of the partition. Okay. So these are going to be orthogonal on these vectors will be orthogonal on the characteristic vectors of these sets. So when they sum up to 0 here. So for example, if I take such a vector and I multiply it here, we have some entry here, and you will have, so let's say this will be alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. Okay, so this alpha 1 in perpendicular to, sums up to 0. So the one that is interest is here, alpha 2, alpha 3, alpha 4, alpha 5, sums up to 0 here. So if you multiply this by this, you're gonna get 0. So it's not gonna, the second part says it's not gonna matter if you have here something or if you replace that something by you can add a linear combination of all one matrix such that you basically kill off this part. So you can put your Cij anything, but you want to make it to your favor. So you want to make a Ci, in this case C12, such that it kills off this part. Okay. So what you're going to look at, basically like I said, the eigenvalues are going to be of two kinds. The PVs, which we got, there were two of them, the ones that are constant, and they're going to be the ones that are orthogonal on the parts. And here, I might as well just look at the ones that are going to be orthogonal here and just ignore this part, because I can kill it off. So that's kind of the idea here. And now, what eigenvalues do I get here? What eigenvectors can you think of on the graph at the bottom that sums up to 0? So the graph at the bottom is essentially this. So the graph at the bottom has 4 vertices. How many eigenvalues this graph is going to have? 4. You know 1 for sure. I said you know 1. Get it? 1. Yeah. For sure. So the 1 is going to be constant here, so we don't need that. We want the ones that are not 1. What are they going to be? Well, there's going to be another 1, because here the complete graph by itself, the spectrum, like K2, what is the spectrum of K2? 1 and minus 1. And here we have the spectrum of 2 K2s. So it's going to be 1 with multiplicity 2, and it's going to be minus 1 with multiplicity 2. Okay? So I throw one of the ones out, because that's the one. So let's do all the spectrum here. So I can have eigenvector 1, 1, 1. This gives me eigenvalue 1. How can I get another 1? Okay. Yeah, but I want it to be orthogonal on all this. 1, 1, minus 1, minus 1. This also gives me 1. So this is the one that I already consider. I throw it out. I keep this one. And then there are two more. 1 minus 1, 0, 0. 0, 0, 1 minus 1, because I want them to be all linearly, independent. So this, for this graph, the eigenvectors that are basically perpendicular on the all one vector here are going to be the 1, 1 and 2 minus 1s, and these are going to be eigenvectors of the big graph. So for this graph, I had from here, from this PV, these constant things, I get 2 eigenvectors, 2 eigenvalues, eigenpairs. Okay? And from here, I get 3 eigenpairs. And you see here, it's like you will take this eigenvectors, and what if you wanted to see what's the eigenvector on the big graph, what do you put here? You just put 0 and it's going to be. Okay? So this is how you find the spectrum of all these friendship graphs. Like here I just give it to you with 2 triangles, but you can play this game with 10 triangles, whatever number of triangles you want to do, and it plays the same. The numbers are going to be different. Like here, the eigenvectors here, the eigenvalues here are going to be different because you get a different number for that 2 by 2 quotient matrix. But the ones that you get here, the ones that are perpendicular on the parts of the partition, they're going to all look of this form, and you can count how many there. So that will be. So what exercise are we? 18, 19. So find the spectrum of K triangles meeting at one vertex. Okay. So again, in some situation, the graphs are more complicated, so it may be hard to find the second part of the eigenvectors and so on. But the ones from the quotient matrix, again, as long as you can get your hands on the eigenvalues of the quotient matrix, that should work out. Those are the ones where they're constant on the parts. Okay. Let me see. I'll just give you one more example and then we'll finish. So for the Peterson graph, let's just do two side by side. So when you did the partition into two parts, we had the quotient matrix, what was it, 2, 1, 1, 2. And what do we get? Here it's easy because the row sum is 3, so it's going to be 3 you get as an eigenvalue. And then it's the trace minus, so you collect 3 and 1. Okay? If you do the partition into 3 parts, we had this matrix 0, 3, 0, 1, 0, 2. Okay, so the same as before, because the row sum is 3, you get 3, and you need to find 2 more. If you like, you can do characteristic polynomial, or then you can look at the trace. So if I have two other eigenvalues, let's call them theta 2 and theta 3, the sum of them plus the 3 will give me the trace here. The trace is 2, so the sum of them is minus 1. The product of them, what's the result, the product of eigenvalues and the determinant? Yeah, but what's the relation between the determinant of the matrix and the product of the eigenvalues? They're equal, or there is a sign? Okay, so you tell me what is theta 2 times theta 3. So let's see, what is 3 times theta 2 times theta 3? The determinant or minus the determinant? The determinant. What is the determinant here? Well, you expand, you like things with zeros, so you expand here, so it's minus 1, minus 6. Minus 6, so theta 2 times theta 3 minus 2. Can you think of two numbers, you sum them up, you get minus 1, you multiply them, you get minus 2? There you go. 3, 1, minus 2. So here 2 parts, you didn't catch everything. Here you catch 3, 1, minus 2. And it turns out that 3, 1, minus 2 are all the distinct eigenvalues of the Peterson graph. They're multiplicities, but we can do that later. Okay, I'll show you later. Okay, I'll stop here. I'm a bit early, but I'll stop here before so in the afternoon we'll start talking about eigenvalue interlacing, so we'll build on this and try to learn about interlacing. Okay, thank you.